Hi, Honors Chemistry. This is Unit 7, Stoichiometry. We're going to begin learning the limiting reactants. How do we figure it out? It's the thing you're going to run out of first. Sorry, spoiler alert. The limiting reactant, like I just said, is what you're going to run out of first. So in that way, it limits how much stuff you can make. So this is my recipe for vegan cupcakes. You need 1 box of Duncan Hines yellow cake mix. Check the back, make sure there's no eggs or milk. You need 1 can of pop. It can be anything as long as it's not diet. And then you need 1 container of Duncan Hines chocolate fudge frosting. Once again, check the back, make sure that there's no eggs or milk. But look at what I actually have in my kitchen. Not enough stuff. I only have half a can of pop and 3/4 of a container of frosting. Oops. So the excess reactant is what we're going to have left over. Just like the limiting reactant is what we're going to run out of, the other thing you're going to have left over, and that's the excess reactant. So which one are we going to run out of first? That's kind of how I think about this. Well, since I only have 1/2 of a can of pop and I need a whole can, that's what I'm going to run out of first. The second thing would be the frosting. But I have enough of the box mix. So that's actually my excess reactant. So a recipe isn't so different from a chemical reaction because they're kind of the same thing. They're just written on the page differently. So this is like fraternal twins. They look alike, but they're in the same family. I'm sorry, they look different, but they're in the same family. So here's our first example. When hydrogen gas reacts with oxygen gas, water is produced. Ta-da! How much water can be produced if you have 4 grams of hydrogen gas and 6 grams of oxygen gas, according to the following chemical reaction? Well, you can't just look at the number of grams and think of, oh, well, I have 4 grams of hydrogen and 6 grams of oxygen. The one I have the least amount of is hydrogen, because that is not how chemistry works. We have to convert to moles, and we have to do kind of a 5-step process to figure this out. So here's our problem again. Here's our reaction. And then these are the 5 steps that we're going to use. The first one, we have to convert grams into moles, and that's what we're going to call our half number. The second step, this one is a little bit weird. We're going to compare the number of moles in each reactant, and we're going to use a mole ratio that we get from the equation. That's going to be our need number. The third thing we're going to do is we're going to compare the half number to the need number. The fourth thing, we just have to determine which one is the excess and which one is the limiting. And then the fifth thing that we're going to do is we're actually going to solve the problem based on the limiting reactant. So here's our problem again, and we're going to do the first step of it, okay? I've got 4 grams of hydrogen gas and 6 grams of oxygen gas. Step number 1, to find the half number, I simply have to convert these into moles, which is really easy. You got to have your periodic table, but it's the easiest step. And you can see that I had a few more moles of hydrogen than oxygen. The second step is where I'm going to compare both of these reactants to each other. And I'm going to use the mole ratio from our equation. So where did I get 1.98 moles of hydrogen gas and 0.188 moles of oxygen? From the previous slide. That was the very first step that I did. And now I'm going to use my mole ratio comparing the moles of hydrogen to the moles of oxygen right here in this equation. That's how I'm setting it up. That's where I got 2 moles of H2 from and 1 mole of O2. That's where that came from. And when I solve this, these two things become my need numbers. This is how much I actually need to make that reaction happen. It would be like the actual recipe on the box. Okay, this is steps 3 and 4. They kind of happen together. So you can see that all I'm doing is I'm using greater than and less than signs to compare how much I have to how much I need. And if you look at hydrogen gas, I have 1.98 moles, which is bigger than 0.376. That means I'm going to have that left over. And that means that oxygen is actually my limiting reactant. So now that I know which one is the limiting reactant, since it's oxygen, I'm going to go ahead and use that number from my problem, 6 grams of oxygen, and I'm going to solve this just like I did last week. And I'm going to put in the mole ratio from the problem, just like we did last week, to where I can figure out how much water can actually be produced. So from my problem, you can see 4 and 6, that's only one significant figure. So my answer has to have one significant figure. And if I'm looking at 6.756, if I round that up, it's 7. All right, second example. When propane gas and oxygen gas combine, they combust to form water and carbon dioxide. If I have 30 grams of propane and 30 grams of oxygen, how many grams of carbon dioxide can be produced? Well, step 1, all I'm going to do, the easiest thing is just convert from grams to moles. And this time I tried to mess with you a little bit. I wanted to show you, you can have the same number of grams of something, but it's not going to be able to tell you whether or not you have the limiting reactant. To do that, you have to convert to moles. The second step is where we're going to compare both of our reactants to each other using our mole ratio. So I'm looking at oxygen and propane. That's propane, that's oxygen. I'm going to compare them. And 0.680 and 0.938, I got that from the previous slide. And I'm just going to use my mole ratio to solve. And when I do that, that's going to be my need number. So that means I actually need 3.4 moles of oxygen and 0.188 moles of propane to make this actually happen. Okay, so this is step 3 and 4. If you're looking at propane, I have 0.68 moles, and I only need 0.188 moles of propane. That means I'm going to have plenty of stuff left over. It's going to be the excess. But if I'm looking at oxygen, I have a lot less than I need. I need 3.4 moles to make this happen, but I have less than 1. So that means oxygen is going to be the limiting reactant. I'm going to run out of it first. And once again, if this is hard for you conceptually, just look up at the steps and look at how I'm using my little greater than and less than signs. And that might be a little bit easier for you. Okay, last step. Now that I know that oxygen is going to actually be my limiting reactant, I'm going to use that number to solve this problem because it's asking me how many grams of carbon dioxide can be produced. So I'm going to use the number 30 grams of oxygen, and I'm going to solve this problem just like I did last week. And you can see that I put my mole ratio right in the middle, and I got that from my chemical reaction, 5 moles of oxygen and 3 moles of carbon dioxide. Those are the two things that I'm comparing. I want to see how much carbon dioxide I can make from the amount of oxygen that I have. Now in this problem, we only have one significant figure, so you can write this as like 20 or 2.0, or I'm sorry, 2 times 10 to the first. Okay, this is a new problem. And we're going to look at when you react butane with oxygen, carbon dioxide and water are produced. If you have exactly 55 grams of butane and 55 grams of oxygen, how much water can be produced from this combustion? So step 1, the easiest one, we're going to find the have numbers. And that's where we take the number of grams we have and we convert them into moles. And now we're going to do our second step, which is where we're going to compare the number of moles of each reactant to each other. So this is where we have to use our mole ratio. We're going to compare oxygen to butane in this problem. And that's going to be our need number. Now it's time for step 3 and 4. When I compared the amount of moles of butane I have to how much I need, I find that butane is excess and my oxygen is going to be limiting. So now I can just do my math based off of my limiting reactant. And that means I'm going to use 55 grams of oxygen to solve this problem, just like we did last week. And you still have to use your mole ratio because this time you're comparing how much water you can make from how much oxygen you were given. Okie doke. So, yay, I know that this is tough. Don't give up, chemists try. And look at teams to see your next homework assignment. Bye.